Hi, this presentation will cover the area interpretation of barycentric coordinates. It gives a very nice graphical way to picture the meaning of the barycentric coordinates alpha, beta, gamma of a point U, especially when U is in the interior of a triangle. We're in the situation where we have 3 points, x, y, z, non-collinear. They're the vertices of a triangle T in RS, S greater than or equal to 2, and we'll let the area of T, the area of the triangle T is D. Let's draw a picture here. So here's X, here's Z, here's Y, here's our triangle T, as area D. There's a point U is in the interior. And we're going to draw 3 triangles inside T. There's a triangle with area A here, a triangle with area B here, and a triangle with area C there. So the 3 indicated triangles drawn in the figure have areas A, B, and C. And with U strictly in the interior, all these things are non-negative, positive areas. Then we let alpha, beta, gamma be the barycentric coordinates of U. And the theorem is that alpha is equal to the ratio A over D, beta is equal to the ratio B over D, and gamma is equal to the ratio C over D. So to figure out what this means, remember we have U equals alpha X plus beta Y plus gamma Z. So we're saying the coefficient on X is the area A divided by area D. It's the fraction of the area that's taken up by the triangle A inside the triangle D. Likewise, beta, the coefficient of Y, is the ratio of B to the area D, and gamma, the coefficient of Z, is the ratio of C to the area D. So we get very quickly a good picture of how the approximate values of what alpha, beta, gamma should be in terms of areas. I'll prove this on the next board. It'll be based on the proof from the previous lemma about the existence of alpha, beta, and gamma. So let's give a proof of the theorem. First, I'll start by redrawing a small picture here for you again. We've got the triangle with vertices X, Y, and Z. Point U is in the middle, and we've got 3 triangles, A, which is opposite the vertex X, B, which is opposite the vertex Y, and C, which is opposite the vertex Z, and the whole triangle has area D. So the way the construction worked in the previous video, proving the existence of barycentric coordinates for U, was we built the following construction. Here's our triangle again, with vertices X, Y, and Z. Here's U, and we drew the line through U and Z it intersected W on the line XZ, and W was equal to lerp x, y, b for some scalar b. And that, of course, was 1 minus b times x plus b times y, just by the definition of lerping. And we called 1 minus b, we called a, and so it's the same as ax plus by. So that's the formula for W. We're going to use this to create two new triangles inside T. This will be triangle D2, and this will be triangle D1. And we'll use D2 and D1 as also the names for the areas of those subtriangles. So notice that D is the union of D1 and D2. We have the area D is the sum of the areas D1 plus D2. But we can actually do better than this in terms of characterizing this. Let's consider the lengths of these two subsegments from X to W and from W to Y. If the total length from X to Y is L, then this will have length B times L, and this will have length A times L. And the reason being is that when you lerp X, Y, B, that means going fraction of the way from X to Y, fraction B of the way from X to Y. So we go fraction B of the length from X to Y, we've gone distance B times L. And the rest of the distance is A times L. Now, using the base times height, or 1/2 base times height formula for triangles, using the 1/2 base times height formula for a triangle area, we're going to think of we're going to look at the three triangles D, D1, and D2, or T, and these two triangles here. We'll take the line segment XY and use that as the base of D, and then this will be the base of D1, and this will be the base of D2. All three triangles have the same height from the base because their apex vertex is Z, and their bases all lie on a common line. So therefore, this gives us that D2 is B times D, because D2 has the same height as D, and the length of the base is only B times the length of D. Likewise, D1 is A times D. So for the second part of the construction, let's draw another picture here for the second part of the construction. Here's the same triangle again, with vertices X, Y, and Z. And now we have still the line through U and W. And now we're going to form yet more triangles. And so this is the triangle B, it's the one opposite Y. This is the triangle A with area A, it's the one opposite X. And I'll call this one E1, as this triangle E2. So I'm using E1 and E2 also as the names of the areas of those triangles. So we had that U was lerp WZD for some scalar D in the previous proof. So that means then that by the same reasoning with triangles, we have that E1 is D times D1, B is C times, A is C times D1, where C is 1 minus D. Because we're taking E1 and A as subtriangles of D1, and we've been lerping along the base by fraction D. Likewise, E2 is D times D2, and B is C times D2. These are ones, let me make that clear. So finally we had that U was equal to AC times X plus BC times Y plus D times Z. And AC, BC, and D were the barycentric coordinates alpha, beta, and gamma of U. So alpha is AC, and A we can take as, from this equation, is equal to D1 over D. And C from this equation is A over D1. And that's equal to A over D, which is what we wanted to prove the theorem. And the rest of the calculations are similar. Beta is BC. It's equal to D2 over D from this equation times D2 over D, C. Here we are, B over D2 by that equation. And that's equal to B over D, which is what we wanted. The final thing we needed was gamma, and gamma is 1 minus alpha minus beta. So that's equal to C over D, since A plus B plus C equals D. And that proves the theorem. So on the next board, we'll do an example of how to use this theorem to compute barycentric coordinates. So let's use an example, and we'll do this in a way that's easy to do by hand. It's not the way really recommended for a computer program to do it, but it's an easy way to do it by hand. And it is specialized to work only in R2. It doesn't really work in higher dimensions, although you can adapt it to work in R3 without too much trouble. So let me get a triangle here. So I'll take x equals 0, 0, z equals 3, 1, and y equals 1, 2. And the point U will equal 1, 1. Let me draw a little more to scale. And the question is, what are the barycentric coordinates of U? So what we want to do is we want to know the areas of these triangles here, right? These are supposed to all be straight lines. So the formula we're going to use for triangles is the following. It's based on the determinant of a 2 by 2 matrix, or it's similar to cross product. If I have, here's the general principle. If I have two vectors, U and V, maybe that. V, here's U. If I take the parallelogram that has U and V as sides, so think of this as being another copy of V, this as being another copy of U, the area of the parallelogram is the determinant of the matrix, the determinant of the matrix U1, U2, V1, V2, where U is the matrix, the vector with components U1 and U2, and V is the vector with components V1 and V2. So this is the area of the parallelogram, so the area of the triangle is half that. So the area of the triangle is 1/2 the determinant of, and sometimes we'll use a block notation for determinants. U vector, V vector means put in the column vector U1, U2, and put in the column vector V1, V2. And that gives you the area of either of those triangles, right? So let's work this out. So the area D of the whole triangle, well, let's find the vectors on the sides. This is rather easy in this example because I picked one of the corners to be 0, 0. So this is the vector 3, 1. This is the vector 1, 2. So D is 1/2 times the determinant of 3, 1, 1, 2. And a lot of times we'll write determinant with just vertical bars, 3, 1, 1, 2. And so that's equal to 1/2 times 6 minus 1, which is 5/2. The area B, let's work on B here. So remember, this is B because it's opposite Y. And it has one side is 3, 1. And the other side is 1, 1. So area B is 1/2 of 3, 1, 1, 1, which is 1/2 3 minus 1, which is 2 twos or 1. C is, where's C? C is here. It's the triangle opposite Z. So C has the sides with vectors 1, 1, and 1, 2. So it's 1/2 times the determinant of 1, 1, 1, 2. So that's 1/2, 2 minus 1, which is 1/2. So now we can read off at least beta and gamma immediately. Beta is B over D. B is 1, D is 5/2, so that's 1 over 5/2 equals 2/5. Gamma is C over D, so that's 1/2 over 5/2, which is 1/5. Now alpha we could do the same way with getting the area of the triangle A, but here we can actually take a shortcut. Alpha is 1 minus beta minus gamma, so it's going to be 1 minus 2/5 minus 1/5, which is 2/5. And that's the calculation. So this method, as you can see with determinants, this simple method with determinants works only in R2. You could do something similar in R3 with cross products. You could take the cross product of two vectors and take its magnitude and then divide by half, and that'll give you the area of the triangle with those two vectors as the side. In higher dimensions it gets more problematic, but this method is perfectly good, especially for 2 dimensions, R2, and pretty good for R3. The next presentation will discuss a better method for computers to do this computation. That's the end of this presentation. Thanks.